starting today, we're going to go over functional groups and also, hopefully by the end of today, if not Wednesday, start doing reaction mechanisms. Okay. So functional groups. Remember, a functional group, what you can think of as a functional group is just anything that's it adds functionality, but it adds some new aspect to something once it's added on. And so, I can't do an example of something. We've already talked a little bit about an alcohol, for example, what is a functional group? What does an alcohol look like? Right. Oh, whoops, I'm in the wrong one. Right, that's just the OH, or OH. This right here is not an alcohol. And so that's why I didn't want to point that out and say, oh, what is this? And have you say it's alcohol. What you're going to find out is that's a carboxylic acid. Okay, because it's connected to this right here, which is called a carbonyl group. It's also called an acyl group. Okay, and so whenever you have the alcohol with that carbonyl or acyl group, and it's no longer an alcohol, and that's because there's resonance between those two oxygens. It's carboxylic acid. Okay, so that's just one example. All right. So typically, alkanes themselves are considered inert, right? So they can combust, so that's why, methane can be burnt, or propane, or octane, but you have to add energy to them in order to get to us. Otherwise, for the most part, they're inert. Okay? So what happens is you can start adding things on that can add functionality to them. Now, alkenes and alkynes, they do have functionality, so there are reactions that can occur with them. So that's why they are considered functional groups in themselves. In this chapter, we're going to talk about alkyl halides and alcohols. And if you notice, see it says R and then something else, like RX. That's the generic form. And so, as I mentioned early on, like I think the very first day, we're in the 10th edition, every edition of this book has a typo in it in that table. This one it still hasn't been changed. This is the generic formula for an alkyl halide. And I'll show you the mistake that they made. X just means a halogen, so it can be fluorine, bromine, chlorine, or iodine. Acetine is not considered a halogen here. Okay, so we don't have to worry about that. Whereas this could be, R just means it's any carbon-containing group. Okay, so for alkyl halides and alcohols, R has to be some type of carbon-containing group. It's just the generic formula for it. There's something called an arene, which for those of us with accent sometimes comes out sounding like it's Aryan. No, it's not like, Germanic power or anything like that. It's arene, and arenes are where you have rings that alternate single, double, single, double, single, double, single, double, and so on and so forth. Okay, so this is that table. It takes up 2 or 3 slides here. These are the ones that you need to memorize, because once again, you're just memorizing them just like you would the alphabet. It's essentially like the alphabet of organic chemistry, just like for those who have me biochem, or will have me biochem, we talk about the amino acids being the alphabet for biochemistry. But these are very important. You can't really do organic chemistry without them. Okay? So this is the typo that I point out every year. See the generalized abbreviation? There's a typo here. It says the generalized one is RCl when it should be RX. They had it right on the earlier slide, but they've never fixed it there. RCl is a specific type of alkyl halide. It's a chloroalkane. Okay, so that's why it should be RX, because the X can be fluorine, bromine, chlorine, or iodine. The ones that are most, we won't go there. Okay, but yeah, anywhere from fluorine through iodine. So alcohol is the very first one. It's ROH. Once again, R can be any carbon-containing group. The exception being is R cannot, for alcohols, or for alkyl halides, cannot look like this. in that instance, because it's no longer an alcohol. Once again, that's a carboxylic acid. We'll see it. It's going to be further down on the table. And the original book, this is a long table. It takes up almost like an entire page. And so, unfortunately, it doesn't all fit like that on the PowerPoint. Okay, so ROH is an alcohol. This is just a specific example, and this is how to name it. We already knew this. We've already talked about ethanol. And we'll go over naming in a moment anyway. Alkyl Halides are RX. A specific example right here is chloroethane. We can have an amine, and I want to point something out here too. Technically, this is correct. You see where it says RNH2. However, what you're going to find out next semester, which we don't cover amines in any great detail until next semester, but technically it can also be this. Okay, so the RNH2 is the simple amine. It's called a primary amine. But don't be alarmed. So, for example, I'm just going to move this over here and move it back. For example, whoops, that's supposed to be just a regular carbon. That's an example, another example of an amine. It's just called a tertiary amine. I just want to point that out. See, it's a nitrogen that just has carbons hanging off of it. That's another example of an amine. And so I just wanted to point that out right there, just in case you see it in, because I don't, I pick the quizzes or the suggested problems, but it's from a pool, and so they may pop up something that's a nitrogen, it's got 2 carbons hanging off it. That still is a type of amine. We have an epoxide, and epoxides and ethers are very similar. This, and I also want to point out here, if I were writing out the generic form, I would write it out ROR prime. And the reason why is the 2 R's can be different. They don't have to be the same thing. Usually naturally occurring ones, they are. I shouldn't say naturally occurring ones. Usually, or many times they are, but they don't have to be. An example of the ether they give you is diethyl ether. An epoxide looks an awful lot like it, except it's cyclical. Please note, right here, they've got it looking like this. But it is possible to have an epoxide where they're not in contiguous carbons. So another specific example would be this right here. Whoops. Okay. See, we have an extra linking carbon between them. Usually, if it gets more than 2 carbons away, instead of calling it, they'll just call it an ether. But an epoxide can usually, almost always, they're on adjacent carbons, but they can be 1 carbon removed. I just wanted to point that out. We cover epoxides in greater details later on. We have nitriles. Nitriles, we have an R, which once again can be any carbon-containing group. A carbon triple bonded to a nitrogen. I like to refer to the nitriles as like the red-headed ugly stepchild of the functional groups, because you're going to find out how they're made next semester, and they don't get hardly any time in the coverage within the book and everything. They're actually made from carboxylic acids or carboxylic acid derivatives, but it's like they're mentioned and then they don't go into great detail, whereas they do with all of the others. Then we have nitro, because that's a nitro group. We have nitro alkanes. We have a sulfide, and please notice, this is an ether. This is a sulfide. Sulfide is RSR, and once again, the R's do not have to be the same thing. Another example of a sulfide could be this. Okay, that's an example of a sulfide. And then we have a thiol, which looks just like an alcohol, except it's got a sulfur instead of an alcohol. You're going to find out in vivo, if you go on to take biochemistry, sulfur is very, very important. Okay, in organic chemistry, we talk about it some, but they really focus more on oxygen. But you're going to find out that in vivo, our bodies utilize sulfur a lot. for doing the chemical equation, or chemical reactions, I should say. And the reason being is sulfur is a better nucleophile, is better at attacking things than oxygen. It's also a better leaving group, so it's better at leaving. And so that's why in vivo, under the conditions that our body utilizes, sulfur is just better than oxygen. All right. Now, oh, there's a typo on this one. I didn't even catch it. This is wrong. Wait a minute, let's go here. You can still see it. That one's wrong. This is what it should look like. For a ketone, like the specific example is correct. They just showed you a nitrile again. Ketones and aldehydes are identical, except in aldehyde, the carbon to oxygen double bond has to be attached to at least one hydrogen. Whereas in a ketone, you can't have any hydrogens. And you're going to find out the chemical reactivity between aldehydes and ketones are a little different. So that's the reason why they're considered two different functional groups. This, and I've already said it before, and you'll probably hear me say it over and over again, that carbon-oxygen double bond, many times we call it a carbonyl group, or it's also called an acyl group. Especially in biochemistry, we talk about acylation or acetylation, which is just a very specific type, acyl group, versus saying, well, I mean, we don't ever say aldehyde, well, I mean, because you can't do aldehydylation, you know, it just doesn't work. And so we'll talk about acylation versus making something an aldehyde or a ketone. And so carboxylic acid, technically we have our R group, we have an acyl group, or carbonyl group, if you want to think of it, and then an alcohol. However, this is not a ketone, and this is not an alcohol, because together they form a carboxylic acid. And it's very important, and the reason why is when you draw it out, you can imagine, whoops, I did it wrong direction. Those electrons come down here, boom. Those bond breaks, boom, and that hydrogen can go from from oxygen to oxygen. And so because of that, there's resonance. You don't have resonance if that was a carbonyl group or just an alcohol group. So that means that they have special chemistries all to themselves. So that's why this is not a ketone with an alcohol. This is a carboxylic acid. I want to just say that over and over and over again. Okay. Next one, we have an acyl halide. See, they got it correct here with an X, where it's an R group. Obviously, if this is organic chemistry, the R group is going to be a carbon-containing compound. We have an acyl group and then a halogen. That's why it's called acyl halide. This is a very specific one. We have what's called an acid anhydride. Sometimes some books call them carboxylic acid anhydrides, because once you get to organic chemistry, biochemistry, you're going to find out there are other types of anhydrides. Okay, one called mixed anhydrides and phosphoanhydrides and things like that. But in organic chemistry, we only look at the ones that are carboxylic acid based. So it's an R group. And once again, these two R groups could be different. Many times they're symmetrical, but they don't have to be. But it's an R, a carbonyl or acyl group, an oxygen, carbonyl or acyl group, and then another R. Okay. The next two, I'm going to write out a little differently. Ester which I always point out, I know it's a stretch for faith integration, but it's spelled differently than Queen Esther. Okay, Esther in the Bible, whoops, is spelled E-S-T-H-E-R, Esther. The chemical one is E-S-T-E-R, ester. So, what's an example of an ester? You probably didn't think about it if you just heard it in the name. What? So a phosphodiester backbone is a type of ester. It's a phosphate-based one, which we talk about all the time in DNA and RNA and things like that. Yes, that's true. We don't talk about it too much in organic chemistry because they forget phosphorus until you get to biochem. But yes, but usually people think of like the granny pants, you know, the polyester pants that, you know, like every grandmother has to own. Polyester pants is just literally a bunch of esters that are used to make a synthetic, you know, make that slick 70s looking kind of chic. Whereas now, most of your grandparents probably weren't, you know, well, that's just not the point. But, yeah, you know, I don't know when your grandparents were born, but they were alive in the 70s. But in the 60s and 70s, polyester was really all the rage. So, yeah, that's just really, literally means many esters that are linked together. But I always want to point out is, once again, just to get the idea, that's an R, an acyl group, an oxygen, and then another R, which I'm going to call R prime, because once again, the two R's don't have to be the same thing. So one example, and we're used to reading things from left to right, but remember, that directionality is forced. So what I mean by that is this is still an ester, because even though it goes in a different order, it goes R, oxygen, carbonyl, R group. That's still an ester. Or you could draw it at 90-degree angle to that, and it would still be an ester. And so we just get used to it. Sometimes people don't recognize the functional group because they're used to looking at this table and thinking, okay, alkyl halide has to go RX, and then forget that it could go XR, or it could go up and down. And then I want to draw the amide. Please don't confuse amine and amide. Just like ester and ether. Okay? So in amide, we have an R, the acyl group, a nitrogen, so it's a lot like an ester. And then I'm going to draw it this way. R prime and R double prime. Those can be hydrogens. You're going to find that out with nitrogen. Sometimes nitrogen R groups can be hydrogens, but they don't have to be. They could be all three the same carbon groups. They could be all different carbon groups. And so that's why if we look at this, that compound right there, kind of skipping ahead, but just because I want to point it out, this right here is an amide, because there's our R group, acyl, nitrogen. It's got one hydrogen hanging off that you don't see because it's implied. But it's got one hydrogen here, and then it's got another R group. But it also has, what's functional group is this one right here? What is that functional group? You already learned it. That's an alkene, okay? It's a double bond. And then this one right here, by the way, it's a benzene ring. It's an arene one, which we talk about much more detail later this semester and a lot next semester. But this right here, this is the important part. That's an amide. Once again, an amine, like we could turn this into an amine, and you're going to actually find out next semester how to make that into an amine. But it's going to look like this. That's an amine, because it's missing the acyl group. So amine, whoops, sorry, this is my right hand, amide. And for those who are in biochemistry, it's the same thing as an amino and amido. Just in case I ever revert and say amino group, it's the same thing as an amine group. Okay. Is that it? Yeah. All right, so I'm actually going to, let's just do some examples. Okay. So the compound on the right, I'm going to start off with. This is an amino acid that's common in biochemistry or biology. This is methionine. Okay, this is methionine. Does anyone know, from, if you remember from genetics or biology, why is methionine, besides being an amino acid that's used for proteins, what is so important about methionine? The start codon. Yeah, it's the first amino acid that's always coded. Technically, it's called the formyl methionine, which is a little different than this. But yeah, so that's one of the reasons. But let's just point out the different groups. So we have, there are 3 functional groups that's important on methionine. We have this first, well, I'm going to call it the first one, but we have this one. So what functional group is that right there? Carboxylic acid, which I'm going to abbreviate as carb acid. Then we have this one right here. What is that one? It's NH2, and it's got technically, see, it goes R, nitrogen, and then hydrogens hang off of it. What is that one called? Amine, which, by the way, that's why amino acids, every amino acid has an amine group. Oh, see, I put amino, sorry. Because it's biochemistry, that's what we call it. It has an amine, it has a carboxylic acid. So that's where the term amino acid comes from. Then we have a third one. We have this down here. Notice it goes R, because that's a carbon, S, and R prime, because it's got another carbon-containing group hanging off of it. So what is that one right there? It's not a thiol, sulfide. I deliberately wanted to pick a couple that were kind of confusing, because if it's a thiol, which there's an amino acid that has a thiol, that's called the R group, that hangs off of it. It's called cysteine, okay? Not cysteine as in chapel. That's kind of faith integration. But cysteine as in for forming disulfide bonds. But a thiol, so that's a good review. A thiol goes R, S, and then what comes next? H. See, this one's got a methyl group, and then these are carbon-containing groups. So that's why technically it's a sulfide. And by the way, just so that you would know, maybe you find this interesting, I don't know. Or if you take biochemistry, you would. Methionine is actually used to make, especially some people may take vitamin supplements or energy supplements that say like Adomet. Like it may say Adomet or SAM, S-A-M. Well, that's based off of methionine. And what it does is it's part of your B. It's part of your B vitamins, and it donates a methyl group because it's really hard in vivo for us to move methyl groups, but methionine can. And whenever it becomes a thiol, it's called homocysteine, and it's actually if that gets out of whack, it causes heart disease. So homocysteine is actually utilized. The thiol version of it is utilized to monitor heart disease. Okay, this next one. This is technically called a. I'm not gonna. This right here is a monoglyceride. Sometimes they're called MAGs. But you probably heard triglycerides or triacylglycerols. Oh, just saying. Yes, Bradley.
For the MAGs, so for each of the amino acids, is it basically just different for the other group, like the tail?
Yes, and it's called an R group. And so, yeah, all the 20 naturally occurring amino acids, when you take biochemistry, they only vary in their R group. The backbone is the same for every single one. Okay. All right, this is called a MAG because you've heard of triglycerides. What are triglycerides? Well, are they really bad? What do triglycerides do in your body? What are they used for? Energy. Okay. In fact, what's the number one energy source in your body? Is it sugar? Is it fats, lipids, triglycerides? What is the number one, the best energy source for your body? The lipids. Triglycerides, by the way. And so you'll find out, right? They get the bad rap, and they only get a bad rap, especially in Western diets, because we eat things that are just really high in these. But this is when, as the bonds get cleaved off, like a triglyceride actually has a long carbon-containing group off of this and off of that way, and that's why it's called triglyceride. When it first gets cleaved, then it's called a diglyceride, and when the second one gets cleaved, it's called a monoglyceride, monoacylglyceride. So this is a MAG, because I didn't want the triglycerides get really big, and I didn't want to put it all out there. Okay. And so we have different functional groups hanging off of it. So we get to practice. What's this functional group right here? Alcohol, and this one? Alcohol. What about this up here? I think someone said it. Say it with conviction. It's not an ether, because what do ethers look like? Ethers go R, O, R prime. So it's very similar. That's why I wanted to point this out. And by the way, you do have some types of glycerol-based, this is glycerol ones, that are ether-based. Like, I think it's plasminogen, that's an ether-based one. But not all of them. So what is that functional group? If it's not an ether, it's an ester. Because once again, we have an R, an oxygen, an acyl group, and then another R group hanging off. And so that's an ester. Let me change colors. It just takes practice. So just start practicing your functional groups. Now we're going to focus on alkyl halides and alcohols for the rest of this. But I'm just telling you, you want to memorize all of them. Don't be surprised if even the non-alkyl halides and alcohols start popping up in different assignments or quizzes or exams. Okay. Or we can even, I don't have an example here. I could give you a really big compound and ask you, okay, point out 3 functional groups off of this compound. And I would expect you to be able, okay, that's an amide, or this is an thiol, and this is a thiol, or what have you. Or I ask you, draw me an example of an epoxide. Then I would expect you to be able to draw one. Okay, so there are 2 types. I'm going up both of these. Oh, it didn't come up. There are 2 types of naming, and unfortunately, the picture cut off the second type of name, which is the important one. This right here is called a substitutive nomenclature. Which nomenclature, once again, is just a fancy word for name. Of these 2, there's functional and substitutive. Substitutive is the most important. In fact, that's what you can't see, is it says it's preferred. This is kind of like the slang. And in class, I will, with the exception of maybe once in a while saying methyl fluoride, other than that, or like isopropanol. Other than those couple of examples, I don't ever use the functional class because there's just too much stuff for you to have to remember. And as they become more and more complicated, as you see the third one over, 1-ethylbutyl bromide. I mean, it just becomes very cumbersome. Whereas the substitutive nomenclature, once you learn how to do that, naming is half of it. Like either drawing it, knowing the name, or naming it and then drawing it, that kind of stuff. It's like half the battle right there because it uses the locants. It uses those numbers just like what we've been doing so far. I mean, it makes it so much more easy. You've been using it already with saying like, 2-methyl octane. We've already been doing that. I just haven't pointed it out. I just want you to at least know that this exists and also to realize that sometimes on the quizzes that are online, they may all of a sudden pop up a, pentyl chloride, and that literally means an alkyl group that has 5 carbons attached to a chlorine. So when they're relatively simple, it's easy. Like methyl fluoride makes sense. It's a methyl group of the fluorine. But once it's just easier for us here to use the substitutive nomenclature. Because what you do with the substitutive nomenclature is you look for the longest carbon-containing chain, which we have in this instance 1, 2, 3, 4, 5, 6. So therefore, if the bromine was gone and it has 6 carbons, what would it be called? Hexane. So I'm just going to write it down here. Then we just treat this as a functional group, which is called bromo. And we give it a locant, just like what we do with it. And so this is 3, because once again, you always go with the lowest numbers if all possible. So it becomes 3-bromohexane. It doesn't say 1-ethylbutyl bromide. I mean, that's just a pain. So that's what this is showing down here. This is pentane because it's 1, 2, 3, 4, 5, and there's a fluorine group, so it gets fluoro, and it's hanging off of carbon number 1. So this is, whoops, let's just do a few examples. Oh. There's one. And there's another. And the one on the right, those are chlorines, in case it doesn't show up very well. It's not an oxygen, those are both chlorines. I'll give everybody a moment to get cut up. So if we look at the one on the left, what's the longest carbon containing chain that's going to be the root word? 6, and so it becomes hexane. Now we just go through and we look at all of the functional groups. We have this functional group, which it would be called, what is this functional group? It's a methyl. This one would be fluoro. What's this one right here? Iodo. They just drop the ene and they add an O. And so which one comes last? Because I'm really bad at gauging space. Which one comes last in the alphabetical order? Methyl, fluoro, or iodo? Methyl. And so it comes in closest to the root word. And we have to give it the locant. What number is it going to get? Pardon? And so it can be a 5. Okay? Don't be alarmed if you see some books will say that alkyl halides and methyl alkyl groups get the same preference. Okay? At this point in time, I would accept either one. But so let's say that if you gave it a 5, what comes next in the alphabetical order? That'd be closest to that one. Everybody has to do the alphabet now. A, B, C, D, E, F, G, H, I, J, that kind of stuff. So it's I's, iodo. And its number would be 1, and then you can't, I'm going to have to put it down below, but it's fluoro, I can't spell, and its number would be in this way, 4. Like I said, don't be surprised if some books do it the opposite numbering system for the lowest numbers, where they say that the alkyl halide has the same preference in number as the methyl group. Like there's not one higher preference than the other. I'm going to tell you right now, alcohols trump everything that you've learned so far. Okay, but alkyl halide, some books will tell you that it's the same weighting as just a normal 1. And so if they do it that way, then we would see the same thing, is that this would be 1, 2, 3 fluoro. And I used to be real stickler for that, but now I'm not as much. 3 fluoro, what is that, 2 methyl. Is that still numberized? 6, 10, 5. Oh, I think in this time it doesn't even matter, because the other numbering is better anyway, so never mind, forget about that. Okay. All right, so let's go to the second one. What's the root word for this one? Cyclohexane. Okay. And there are compounds that have more or less than 6. I don't know why I just always seem to draw everything in 6. But yeah, that's cyclohexane. And so then we have functional groups hanging off. In fact, I'm going to change it because I didn't realize it did everything. Instead, let's just add that. It's easy to add on. To make it a little differently. So what's this functional group that, since I changed it, what's it going to be called? That's ethyl, and these are chlorine, and they're going to be chloro. Okay, so which one comes last in alphabetical order? Ethyl, and so it's going to go closest. We have to give it a locant. What number is it going to be? 3. And then we have chloro. What else is there? Di. Don't forget that. Sometimes people forget and they miss like half of a point or something. Because you forget that since there are 2, we have to say dichloro. And then we have to give the numbers. And so what would the number be? 1, 1. And don't forget, even though they're hanging off the same one, you have to list the number twice. Because you could also have 1, 2 dichloro, 3 ethyl cyclohexane. So on and so forth. See, naming is easy. So now let's do alcohols. And I'm only going to show you now, on your own, you can look at the functional group like we've already been doing, like ethyl alcohol. We're just going to do the substitutive version. Oh, whoops. Substitutive version. All right, so there we go. It's just easier just to start and give an example. And you may not want to write the end answer until after we've talked about it, okay? So this is, what would be the root word? And once again, don't write the answer down until the very end. What would be the root word for this? It's a pentane, right? I deliberately made one that wasn't 6. Okay, so it's a pentane, and what kind of pentane would it be? Cyclopentane. So once again, don't write this part down because you're going to see why in just a moment. All right, now for an alcohol, and I'm going to write this twice because there are 2 ways that are both acceptable using this. Well, see, I was going to hexane. I'm stuck on hexane. Okay, so we have an alcohol, and then we have, a methyl and our ethyl right there. What changes here is the ending. And so it's no longer an ANE ending. What it's going to be instead, where's my little eraser? Did I have an eraser here? Oh, you're kidding me. I thought I had a little eraser on this, but I guess this one doesn't. Oh, there it is. I was overlooking it. Come on. Oh, well, that just stinks. Okay, so what we're going to do is I'm just going to block it out. You drop that E. And what's the ending for alcohols? All. However, we have to give locants. And alcohols get priority. So that means it's carbon number 1. It's fine if you put the 1 right there. Or you can actually put a hyphen between the N, the number 1, another hyphen, and the OL ending. So that would be cyclopentane, 1-all, or 1-cyclopentanol. Now the rest of it's the same. We now just name this, we name that. We already know that one's methyl and one's ethyl. Which one comes last in the alphabetical order? Methyl, and so don't forget your little hyphens. Methyl. Methyl. Okay, and what's the number going to be on it? 3. 3. And then we have ethyl, and the number on the ethyl is going to be 3 also. So we can have 3 ethyl, 3 methyl cyclopentane, 1-all, or 3 ethyl, 3 methyl, 1 cyclopentanol. So now I'm going to write out the name and give you a moment to draw it or to draw it on your own. Four propyl octane 2-all, which by the way would be the same thing as saying 4 propyl 2 octanol. Okay, so for this one, what's going to be the root? How many carbons are going to be in the root? 8. It's that octane part. That tells you, and it also tells you that there are no double bonds or triple bonds. We haven't really learned how to name those yet, but since it has an AN instead of EN or YN, it's going to have 8, and they're all going to be single bonds. So 1, whoops, that's supposed to be connected. 1, 2, 3, 4, 5, 6, 7, 8. So where does the alcohol hang off? 2. It doesn't even matter which end, as long as I'm going to put it on that end. You could have put it on the left end. It's fine. Okay. And then 4 propyl means hang off of carbon number 4. How many carbons are there? 3. So it's 1, 2, 3. So that's it.